Yes, good afternoon, and once again, I want to welcome you to today's Maniac Talk. Today, it's my distinct pleasure and honor to welcome today's speaker, Vanderlei Martins, who is a professor of physics at the University of Maryland, Baltimore County. And he is also associated with, he's also a researcher with the Joint Center for Earth Systems Technology, JCET. So one of the colleagues who have worked with Vanderlei for so many years, I think they met back in the mid-80s, Lorraine Riemer, who is also a research professor at JCET, is going to help us understand who is Vanderlei Martins since they met more than 20 years ago. So please help me welcome Lorraine Riemer.
Thank you, Charles. I was asked to do this, I don't think because I know you best, but I probably know you the longest, except for Marnez, of everybody in this room. And that was kind of a fluke because he came to visit Goddard for the first time and no one was here because it was a federal holiday, except me. So that's why I got to be first. Anyway, I don't want to tell your stories because Vanderlei's here to tell his stories in his own words. I just wanted to introduce you to Vanderlei as he is now. And as Charles said, he's a professor of physics at UMBC. He's the founder and leader of the Laboratory for Aerosol and Cloud Optics. He's in the process of turning UMBC into a national center for small sats for earth science applications. In doing all this, in the process, he's providing experiential learning for dozens of students, graduate students, undergraduate students, high school students. And by giving them real projects in a real situation, he's boosted the careers of, say, dozens of students, okay, in different directions. Vanderlei is the foremost instrument designer-developer for measuring aerosols of our generation. And this is both in situ measurements, like from nephelometers, and from remote sensing measurements, like polarimeters in space. He's a leading voice for small satellites for earth science applications nationally, probably internationally. And he'll be launching HARP, which he brought here to show you the model, which is a miniaturized polarimeter on a CubeSat platform. So Vanderlei is where science meets technology. That's right there, right where that piece is, in aerosol science. He's forward-thinking, he's a visionary, he's a creative scientist like is very rarely run into anywhere in the world. And with the disclosure that I'm also have a stake in this, Vanderlei is co-founder, majority owner, and chief technical officer of AirPhoton LLC.
Thank you very much, Lorraine, and good afternoon, everybody. So I'm here today to talk about some of my experiences, but mostly I think about the people who I have been working with and the things that we have been doing together since I started as an undergraduate student at the University of São Paulo, in the Institute of Physics of the University of São Paulo in Brazil. And you know, as many other young physicists who I know today, who I have been meeting, who I have been trying to recruit to work in my field, I did not want to work in our field, in the field that I work today. So I really didn't, and I did everything I could to avoid it. And the more I did it, the more I got into it until I'm here today. So that's why I want to talk about, you know, my experience from the atom to the atmosphere and beyond the atmosphere, where we are now doing our measurements. So the inspiration to this talk came from what I just said, right? So the experience that I had as a young physicist trying to find my way, trying to be Feynman, trying to follow Einstein and some other you know, famous scientists, and not seeing what was right around me, not seeing what was very close and things that I could do right there. And as I said, I see that happening today when we try to recruit young physicists to work in our field. They will later on, as I did, much later on, see and realize that there are many other areas and many other interesting things to work with, but it takes some maturity, it takes a while to get there. And I have a few warnings about the talk and about the discussion. So it may be a little bit too autobiographical because of the way this talk is put together. but really was an attempt to be inspirational for young scientists and people who will eventually follow into this field. And as I said, it's all around the people, all about the people that we have around us. So that's really the most important thing, and the more I live, the more I learn about that. And they've been very lucky to bump into the right people and not only stick to them, but have them stick to me, which is, has been really, really important. And then my family, both my family in Brazil and my family here, they had and they still have to put up with a lot for this journey to happen and for things to happen the way I wanted them to happen, for things to happen the way I had them happening. And then the last thing is, since I'm talking about, and I'll show things about other people too, I'm going to miss a lot of people, and several people who are here today, right? And just because there's no way to make justice to the importance of the people I had around. So I just picked a few cases and a few examples and a few discussions, a few things I'm going to show here and there. So for sure I'm going to be missing a lot of people. Not because they're not important, but just because I pick a few examples. So I think the first thing is, going back to São Paulo, right? So starting at Maryland, where I am today, and back to São Paulo, where I lived, more than half of my life. And then from São Paulo, the place where I lived, to the University of São Paulo and the Institute of Physics, where I did most of my academic work, actually, probably all of my academic work. And São Paulo, I want to give you some background on that, because São Paulo is an interesting place. So it's a metropolitan area, something like less than 100 miles in extension, the whole metropolitan area, but fits 20 million people. So you have 20 million people in a packed place, and lots of things happen in a situation like that, right? And between the place where I lived and the University of São Paulo, it's something like 20 miles. So it's 20 miles to get from one place to the other. And if you leave home at 7 a.m., you're going to get to the university at 9 a.m. if you're driving. So if you're driving, you would take at least 2 hours to go these 20 miles from this place to there, just for this, for studying. But that Institute of Physics is a very special place. So it's a place where it's one of the largest in the world. They have, just for the Institute of Physics, 25 buildings. They have around 1,400 undergraduate students and 150 permanent professors in that institution, plus a lot of researchers who are associated with that place. So it's a really good place to be and to learn. And back to São Paulo, as I was saying, a relatively small area, so you have lots and lots of people, right? And just to give you an example, so in the whole Brazil, which we have over 200 million inhabitants, we consume about 1.6 million pizzas every day. But 1 million of those are consumed in São Paulo. So just to, by being a big metropolitan area in a very large place like that, there are things that happen that are unique to those places. So, and you have this ocean of buildings that goes far away, right? Basically, it's not that far, it's not that large area, but it's very densely packed with a lot of people. And then from that, we have this sea of particulate matter, right? So you have aerosols everywhere being produced by cars. It's over 7 million cars in the city driving there every day. And even more important than the emissions that we have there for people breathing the air in the region, it's the inversion. We have very strong surface layer, very strong inversion close to the surface that traps the air pollution there and increase the concentration close to the surface. I have seen cases where that layer is so shallow that it's sometimes below the top of very high buildings. So that's why you get significant concentration near the ground. And as I said, I've been trying to avoid air pollution and work in that direction for a while, but most of what I'm going to talk about is related to that. And just an example, because it's a place full of contrasts, right? And full of contrasts in temperature, in things that happen in the city, and all over. And this is another example. So this is July 10th last year, and we had variation in temperature from the morning to midday or to early afternoon of close to 20 degrees Celsius, variation, just from the morning to the afternoon. And that contributes to this strong contrast we have there, strong shallow inversion layers that trap all this pollution to low levels and increase the pollution problem. But we are actually not that bad, depending on how you compare it with other places, right? So this is São Paulo, and that's Los Angeles, even today, right, or recently. Most of the problem of particulate pollution in the US has been solved, but not quite, right? Not everywhere and not quite. Of course, this is PM10. It's just a particular type of particulate that I'm showing here. But just to place São Paulo in some location, right, and compare it with places where you have, really, really high concentration of this particulate matter. Then, because I'm going to talk about people in general, I want to start with my family, right? So my family in São Paulo, where I grew up, and I come from a very, very poor family. So I was estimating, comparing, and the income that my parents had is about 1,000th of my income today. And São Paulo is not that cheaper than here. Sometimes, for some things, São Paulo is more expensive, right? So I make at least 1,000 times more than what they did. So there are only two options, right? So either they made too little there, and they don't know how they got along, or maybe I'm making way too much, right? So there is one or the other. So we'll try to figure it out. And I really don't know how they did it, because if you compare with things that happen in São Paulo, they were able to build a house, they were able to, own their own property and have the kids being educated to different levels, but having the kids being educated and everything else. So it's really hard to understand how they were able to do it in São Paulo. Maybe in other places you could do it, but in São Paulo, it's a really hard place to do something like that. So they had no formal education, or almost no formal education. Like my mom went for 2 years in the elementary school, and she learned so much in those 2 years, because I remember she teaching me things all the way to high school and following up and helping me with math problems and other things. So I never understood how she got that in those only 2 years of elementary school education. So either they had a much better education before, or maybe she was too smart, I don't know. But something happened there that I also cannot understand. So she passed in 1999, the year I came to Goddard. And then my dad, he actually never set foot in a school. So he never has been to school. And nevertheless, both of them, made sure me and my brother and my sister, we had education, we could do the things that we did. And one interesting thing about my dad that I actually only realized a couple years ago was that he actually literally taught me how to make things. And I never realized that until a couple years ago when this flash came back. And I saw he teaching me how to make this car. And it was a car, to play on the street with the other kids. And when he started building it, and he didn't have tools. So he didn't have any tools. So he would make the tools, and he would figure out if he needs to make a hole in the wood, in a thick piece of wood, how do you do that without any tools? So he would make a fire, he would warm up a piece of metal, and burn the hole through the piece of metal, and all sorts of things. And when he did that car, so he was putting the car together, and I was complaining, Dad, why you are doing this thing? The other kids are buying their cars, or they have ball bearings to put in their cars, and we don't have anything, so I don't want this car. And he starts by making the wheel by cutting a square piece of wood. And I'm like, crazy, this is a square piece of wood. How are you going to make the wheel from the car with a square piece of wood? And then he cut the edges, and start to look more like a wheel, but it was not round. And then, Dad, this is crazy. I don't want this. All the kids are going to make fun of me, and I really don't want it. So when I took the car to the street, and he pushed me up, and he pushed me down, and he pushed me up, and he pushed me down, and the wheels start to be round. And after a few back and forths, I had this perfect wheel in the car, and he had a very innovative way to steer the car, and all the kids were crazy about it. All of them wanted it. So my neighbor went to his dad, no, I want one of those, you have to get me one of those. So his dad came to my dad, please help me build one of those cars, because my son really wanted it. And so that's something that I really owe him, because I think I learned some of those things with him, on how to build things, on how to do different things. I just want to say something about high school in Brazil, because this still happens today. And my wife had the same experience. Most of my friends had the same experience. If you come from a poor neighborhood, you have to work. So you start to work when you are, at least maybe 14 years old, but sometimes even much younger than that. So I started when I was 14. I started to work, and I would go to work from 8 a.m. to 6 p.m. That was about an hour away from home, and then another, 30 minutes away from school. And then I leave work at 6 p.m. I would go to school, start classes in high school at 7 p.m. until 11 p.m., take a bus back home, an hour to go home, and then have dinner at home at that time, right? And you start all over again next day. It's not a unique experience. I mean, my brother and sister, I think they start working younger than I did. My wife started working about the same age. So this is, just to give you some perspective on part of the experiences that you have in a place like São Paulo. And I just want to show this because I found this as I was preparing the talk. So this is actually part of the job. So part of the job that I had, I started working at 14, making copies, making blueprints like this, like copying the work of other people. But in a few years, I was actually drawing them. And this is one of the works that I did at that time. I was going from high school, and before I started university, I was designing machines and calculating machines and designing them, and then the company would build them. And it was all sorts of things, all sorts of different machines. So I'm saying because these all contribute to, I think, what I am today and the things that I have been doing today. So just back a little bit to people and putting things in context, right? So when I started university, I was still working from 8 a.m. to 6 p.m., doing those drawings and doing things like that. Now it was an hour and a half away from bus because more traffic and a little further away, right? And school, luckily, was a little bit later, so it was from 7:20 p.m. to 11:20 p.m. And then we also had classes on Saturday morning at the university. And again, University of São Paulo is a very strong university. It's hard to get in. And when you get there, you have to study. You have to do a lot of work. It was a disaster. It was a complete disaster. Like, if I had a student like that today, I would kick the student out. There is no way that a student like me could make it, right? I mean, there's stories there that I won't tell you here because it's a complete disaster. But I liked it. I loved it. So I met people there who are, experimentalists that you have seen there. I never seen people doing what they were doing. And some of other theoreticians that we had in the department also talking about things and inspiring the students in a way I never seen before anywhere else. So I really wanted to do it. So I figured out a way in the second year. I said, okay, this is not going to work. So from 7 p.m. to 11:20 p.m., I'm sleeping. So I'm not, I have a hard time learning anything, so it's not going to work. So I figured out a way to transfer during the day and taking classes during the day, and then do work because we need income for the family. So I was still living with my family and help to support the family. So I had to figure out a way to do it. And that was getting lab fellowships. I mean, there was a saint who gave me a fellowship because with my resume, my grades at the time, I don't know how he did it, but he did. And I learned a lot from that lab fellowship. And then I was doing tutoring, even high school teaching, doing blueprints like that as a private contractor for some companies. And I had to figure out a way to make my journey faster. So I bought a motorcycle, and I could drive between the cars and get to the University of São Paulo faster, right? And then I do need to talk about this professor. So then I met Professor Manfredo Tabachnik. So he was my lab teacher. And I never seen anyone doing things the way he did in the lab, and creating things and making them happen. And it didn't matter the subject. And I couldn't understand. And guess where he worked? So he worked in the air pollution group of the university. And they really did not want to work with air pollution. I knew about that group from the university, but it didn't make sense to me why a physicist would work with air pollution. But he was the best experimentalist I ever met, still is. Right? So I really wanted to work with him. So I decided to follow his steps, despite of his work with air pollution. And I started working in the area that he worked, because I'll show you in a moment. He had another side to it, right? And then following that, I did the master's and PhD in the same place, you know, in the air pollution group, because I really liked the people that I had there, but not quite doing air pollution work. So I did not want it. I was trying to figure out a way to avoid it. And I do want to say one example of the person, right? The person that Professor Manfredo is, and how he treated me, and things that I wish I could learn how to do that with my own students. One day we were in the middle of an exam. It's an exam, the class is full, he doesn't have any TA or anything like that, so he's alone in class, and I'm in the middle of the class, and I'm done. I'm really saturated with the whole thing. I'm working, I'm running from one place to the other, and I can't do this anymore. So I stand up, I said, you know what, I'm done. I'm leaving. I'm leaving, I'm not coming back. I'm leaving the university. And I don't want to do this anymore, I don't need this. I'm leaving. He looked at me, and he looked at the other students in the class, and his answer was, let's go for a coffee and cheese bread. If you know Brazilian families, you know what cheese bread is, probably. So it's something very special that we like, that we love, and that we have all the time. And I look at that, and are you crazy? We're in the middle of the exam. You have the class full of students. You want to go for a coffee? Yeah, let's go for a coffee. So he leaves the class with me and walks to the coffee place. And I didn't understand. It didn't make any sense. But then he told me stories. So stories that he said, you know, these are the stories I tell my kids. And he told me a couple stories. And it was so enlightening. It was so important to me that as a result of that conversation, of that coffee and cheese bread, I went back, I finished the test, I got a high grade, and I'm here today. So I stayed, and that was it, because I was leaving. I was really leaving. And he figured it out, and he left the class. You know, probably the other students were all, at that time, cheating and copying from each other. I don't know, but he went with me for a coffee and saved my career. So I just want to say that as an example, because that's, you know, that's how we make a difference, right? And I really wish I can learn how to do things that way. I just want to show this because that's how I survived, and barely, right? Because it's delicate. All the cars are stuck and stopped, and then the motorcycles are zooming through the corridor. And that's how I was able to do it. So I had to do that. Otherwise, I couldn't either support my family the way I was doing or continue the university. And then when I decided to join that group, and this is a picture way before I joined, but it's for some people who know them. So this is Paulo Artacho in the 70s, and that's Manfredo in the 70s, their advisor and the technician who still works there today and helped them. And this was their pollution group, but a lot of aerosol work started on nuclear physics labs all over the world. I mean, there is very famous work done in many places in the US in nuclear physics labs, like for instance in Davis. There are places at the University of Lund in Sweden, and many fundamental things in air pollution started in nuclear physics labs. And that's how they fished me, right? That's how they got me. Okay, so nuclear physics, yeah, that I could do, right, as a physicist. That sounds interesting. As long as I'm not doing air pollution, you know, I can do the atom part of it and the studies that they were doing there and work with that. And just, you know, this is, again, way before I arrived in that lab. So this is from the 70s. But one of the reasons I'm showing this picture here is in 77, Manfredo was doing his master thesis. And he was running in 77 the experiment of something that was invented, that was discovered by the first time in 76 in Sweden. And he was reproducing. So his master thesis was to reproduce that work that was done the year before in Sweden. And he did that in Brazil. So that's why I'm saying that I think he's the best experimentalist I ever met. I really mean it. So, yeah, it's me. It may not look like, but this is during my master's, when I was doing the master's there. So I took the particle accelerator that they put together and started doing studies, working in their pollution group, but I had to make a deal with my advisor. I do not want to work with air pollution, right? So I told him, let's figure out something else. So if there is something else I can do, I'll do it. But what's the point in studying air pollution, right? So because of that, so we took the particle accelerator, and this is a picture of the lab recently, the lab today. And we made a project, and this was my master's project, which was to study tree rings. So you take trees from the Amazon, and you would extract the core of the trees from the Amazon, and as you can date the rings from the tree, I was studying the composition and the structure of those rings in the tree, and try to associate that with the history of the Amazon, try to associate that with the environment and the place in the region. So took a tree ring, you cut a core either by cutting from the tree, or if you have a piece of the tree, you just cut that core, take a small piece, and then I was analyzing the rings or developing techniques. We didn't have instrumentation to do it, so I had to build the instrumentation so that we could do those analyses and measure the composition and structure of the trees. So basically, you put that piece of wood in high vacuum inside the particle accelerator, which was my first challenge, so that was not easy to achieve. And then you bombard it with high energy, or not that high today, but some relatively high energy proton beam. And then from the interaction between the proton and the wood, we would measure backscattered protons, we would measure X-rays, and depending on the energy, you could measure a bunch of other things. And then the idea was, again, to do that chronology, the endochronology of the wood, and then associate that with changes in the environment. So it was a very successful work. So we did that. We were able to develop the technique, build the apparatus to do it, do all the analysis, and measure several elements. And surprisingly, there were several very interesting variations that happened. And we were also able to date the wood, from about, in that particular one, from 1800 to 1990, when that sample was collected. And we had interesting structure that we found there. So some of them reflecting environmental changes in the region, and others reflecting the biological response of the tree to the environmental change. Like that was what we postulated for the potassium in particular. But bottom line is there was a very successful piece of work, so we learned a lot from the whole process. I learned a lot from the whole process in terms of using that lab and doing this type of measurements. When I tried to convert that to a PhD, because I thought this is going to the point that maybe a PhD, the answer I got was in line with my way of thought, right, in general. So how can this be a PhD in physics, right? Because this is physics, and you are doing like these environmental measurements for the Amazon and things like that. So we couldn't convert it to a PhD, although the work was growing and there was a lot to continue and learn in that direction. So I had to change field, right? So I decided, okay, so if this is not worth a PhD, why am I doing it? And today, I'm sure this is a worth a PhD here in my lab and in other places. So we could do it. So it was something that we misinterpreted at the time. But anyway, just to put some dates. So 99, I actually came here to Goddard. And I may have put this date wrong, but around 2006, I actually moved to MBC and started the LACO lab that Lorraine mentioned before. And in 2014, we started together, Lorraine, Rich, and I, Dare Photon, the company that she mentioned. And I will show you some of these things in a moment. So then I was moving to my PhD work, right? And I still don't want it to be in air pollution. So I cannot do it with the accelerator and the trees. But air pollution, what's the point, right? But I kind of moved to the atmosphere because it looked like we had some very hot topics there. So I called it, atmospheric radiation, particle microphysics, hygroscopicity, remote sensing, and all sorts of things, trying to avoid the air pollution term, right? And we would look at all sorts of particles. So these are all particles that I did during my PhD, and we were analyzing the properties of those particles. So biogenic particles, smoke particles, pollution particles, smoke clusters, dust, all sorts of things. But back to the people, right? So I really think it's all about the people that we have around and the way you interact with them. And as I was putting this together, I realized that 1994 was a very special year, right? And again, I'm missing a lot of people. So please, excuse me here for not mentioning many, many people who are very important, but these are some that I would like to mention at different occasions, right? So definitely, Manfredo, as I said before, then Paulo, who became my advisor for master's and PhD, and we still work very closely together today. Then, in one of those lapses that I wanted again to leave the field because I want to do some more fundamental work, some more physics, some more very fundamental science, and I'm not seeing that in the atmosphere, right? So as a response to that, Paulo sent me to Europe to meet Didier Tanré, Helmut Horvath, and many other people. So he sent me on a tour to Europe. He said, okay, so you want to leave, that's fine. But why don't you go and meet these people, see what they're doing, and then you decide after that. Well, tour to Europe, yes, I'll go, I'll take it. So we went there, we visited many labs, but these are the two that really were responsible for me to continue in this field and to start the work in atmospheric radiation. So I was the first in our group, under Paulo Artacho, to do atmospheric radiation in the Institute of Physics. So today they have, many experts and it's a big group, but my PhD was the first to work in that direction. And really thanks to Didier, who I met there in Lille, and was very impressed with everything that he had there. And then Horvath, Helmut Horvath, I don't know how many of you know him, but it was really an amazing inspiration. So while I was visiting him, so he took me to different places. He took me to the place where Boltzmann had, some of his experiments, which impressed me right away. But more impressive than that was when he took me to his winter house, his winter vacation house. So in Brazil, we have summer, well, we don't, but people have summer houses, right? But he had a winter house, and that concept didn't exist for me, right? Coming from Brazil and traveling outside the country the first time. So he took me to his winter house, and it's a beautiful place, beautiful house, but then I look, and he has all these instruments that he has built that he's using to measure the atmosphere in his winter house. And he has these sensors, and he says, this is how I measure absorption, this is how I measure scattering, this is how I measure this and that. And I was really, really impressed. And again, I was sold more and more to work in this area and to work in this field, although I was still rejecting it as air pollution. But I was very impressed. And then same year, a little later in the year, middle of the year, I came and I met Yoram by the first time. And we were going to the Aerosol conference together in Los Angeles. So I met Yoram in Los Angeles. And Yoram is really the reason that I continued in this field and I'm here today. But the interesting thing is when I met him, so we were walking together from the hotel to the conference, and I'm talking to Yoram, and I barely know English, right? Because it's my first trip outside Brazil, never learned English formally, and it's and there is this guy with Polish accent, right? So Yoram's talking to me, and Paul is talking to someone else behind, and Yoram's talking to me. And he's explaining about this sensor and these things and these measurements. And I cannot understand what he's saying. I don't understand his English at all. And I'm very confused, but I'm trying, right? And I'm asking questions, and I'm trying. And he stopped, and he draws in napkins or whatever paper we had. And we're discussing, and I'm trying to figure out. So years later, because I remember the conversation, so years later, I associated that he was talking to me about average. And the sensor average and mass and all the measurements and all the things that they're going to do for, the SCAR-C, SCAR-B experiment. And as part of that trip, I was going to the SCAR-C experiment. But again, I could not understand his English. It was really, really hard, not because of him, but because I didn't know English. And a couple years later, Yoram told me, when I met you the first time and we were walking to that place, I thought you were one of the smartest students I ever met. And I couldn't understand him. I really didn't know what he was talking about. So it was a weird situation, but somehow it worked. And after that, Yoram invited me many times, and they came to Goddard many times and worked with him. Same year, I met Lorraine, and as she said, so I came in a holiday because I had no idea, right? And it was a holiday. At that time, they let people enter Goddard in a holiday, even if you're coming from another country. And Lorraine is the only person there. And I met Lorraine, and right away, I realized that Lorraine is kind of that lighthouse, right? And many of my friends were seeing the same way, where all these young scientists, saw the light and saw, guidance in the direction to go and what to do. And really, that's how she is until today for me and for many other people who I know. And then many others, right? So we had Brent, and, everybody knows Brent, and great inspiration and model. Peter Hobbs, and I worked with Peter Hobbs, so I flew by the first time with Peter Hobbs in '94 during the SCAR-C experiment, and then we flew again together in the SCAR-B experiment, and he really started me with two things, aircraft measurements, but even more important, English. I didn't learn as much as he wanted, but he really taught a lot in that direction. And many others, right? So Shanna, who you all know, Jeff Reed, Sasha Marshak, Ilan Koren, Keith Gendreau, who probably most of you don't know, but coming from space sciences, really, to me, became kind of a mentor and inspiration to go beyond the atmosphere and do other things that I'm doing, like HARP. And then Leroy, so my connection to the engineering side, right, which still is a struggle to do a good connection with the engineering side, but he really has been the best liaison for me to go in that direction, and he also helped us a lot in building our group at UMBC. So this is what I showed in the Joran Symposium before, but really, I just want to mention it one more time, because I really have to thank him for the ideas, motivation, support, friendship, and for things that really happen thanks to him, right? So there are several things that we work together that today are becoming concrete, are becoming reality, because he was the one who decided to fund it and to push it and say, like a crazy idea, like cloud side measurements. When I proposed it, I heard in the meeting, in an official meeting, cloud side? Why do you want to measure that? Clouds don't have sides. Clouds are planned parallel, right? So they don't have sides. And Yoram was the one who pushed it and who really made that happen. So I just want to make sure I take him for that. And then just a couple highlights I want to show. So from the measurements and from things that we did together. So one of the first works I did here in Goddard was to look at aerosol absorption and back to pollution in São Paulo, right? So we did the measurement and we compared spectral dependence of pollution in São Paulo versus pollution in Wallops, and two types of absorption there. So cases where you have brown carbon and a lot of absorption in short wavelengths in the UV, and cases where the absorption behaves exactly like 1/lambda, and it's just absorption by black carbon. Another work that I did at the beginning, probably at the very beginning here, was a cloud mask, right? So I was looking at MODIS, we're all looking at MODIS data, and realizing that we can't really do good aerosol retrievals because we have a lot of cloud contamination. So one of the first pieces of work inspired by Didier was this 3x3 spatial variability cloud mask, where you can easily identify clouds with a single test. Of course, you need a lot more than that to do a good retrieval, including better other tests for clouds. But this became the basis of our aerosol retrieval at the time. And then, as I was saying before, this is the slide that actually I presented in the meeting here. And I called a couple people because I had this crazy idea. There was going to be an experiment in Brazil, and the experiment was for smoke and cloud interaction. And we had a beautiful aircraft with everything aerosol, a lot of instrumentation for aerosol measurements, and no cloud measurements at all at the first, when they designed the experiment. And then I had this idea, because I was here learning from remote sensing side at Goddard. So why can't we look at the side of the cloud from the aircraft and retrieve the vertical profile of the droplet size and the freezing level, right? Determine where the water freezes and become ice. So I called a few people in a meeting, and Yoram was supporting the whole thing. And I presented the idea with a few slides like this. And, Yoram was the only one who bought into it at the time. So he said, well, maybe we can do it, right? And then I asked for some money to build the instrument. I had no idea how much it cost to do anything in the US at the time. And I asked him for, I think, which to me sounded like a lot of money. I think it was like $20K. And this was to build an instrument to fly in the aircraft in the Amazon for this experiment that was 3 months away from today. So in 3 months, we're going to have the experiment. And I wanted to build an experiment, and asking him for $20K, and he funded it. So he gave the $20K, and we built the instrument. We took it to the Amazon, And it got stuck in customs. So customs didn't let me pass, although we did all the paperwork and everything. And so because of that, we were 2 weeks late into the experiment, but we were still able to get the last few flights, and this is the instrument. So we integrated to the Bandeirante aircraft in the middle of the experiment, so they were already running the experiment. So Danny Rosenfeld had just left that day, and we mounted the instrument in the morning, and we flew in the afternoon. And we collect, from that, we collect a lot of data in the profile of clouds from the side, where we could see the spectrum all the way from UV to 2 micron, and then the vertical profile. So for instance, if you take a wavelength here around 1.6, you can see this is the water portion of the cloud, and that's the ice portion of the cloud, and you can very well see the transition between water and ice in wavelengths where you have absorption. And then many other things, right? So you can get the spectrum in, above the cloud, below the cloud, at the cloud level, and then determining many things. Again, ice and water is one of the simplest examples for that. And that became the basis for later on what we did, the Claim 3D proposal, and several work that I did with Sasha Marshak, Tobias Zeiner, and the others. So this is another example. So this cloud is about 10 miles from the base to the top. And here you have, ice and water in the cloud and the temperature profile. So this was all built as part of that device that we took and flew in Amazon. So this is, all came from those measurements. And here are some more quantitative results, right, where you see now the vertical profile of the droplet size, showing different processes that you have there, and then the freezing, where the particle size in the droplets grow tremendously, and then the ice portion, where in most of our measurements we see it going down as a function of height, and then separation between water, mixed phase, and ice. Very, very clear signal that you can do from the cloud side. These were 3D simulations that we did with Sasha Marshak and Tobias Zeiner to validate and to perform retrievals like this. We had also lots of simulations with other collaborations with Tao's group here in Goddard, where then Tobias Zeiner took that, those simulations and simulated the retrievals for the cloud measurements. As part of that, Lorraine now, and I, and Rich, and Ilan Koren, so we started doing experiments to do cloud side measurements. And I want to tell the story about this one in particular. So this was in Mount Mitchell in North Carolina. So we took the instrumentation we built, and we took it there to look at the clouds. And we are scanning the clouds from the side and measuring it. And the tree is on the way. And I'm cursing the tree. I'm saying, this damn tree is on the way, and I hate it, and it's bothering me because I want to measure right there. And Lorraine turns to me and says, one day you're going to thank this tree. Look at her. Are you crazy? I'm going to thank the tree. It's on the way. And, I have blue sky on the top. I have blue sky here at the bottom. I want to see that transition. Look, there's something going on there. I want to see what's going on there. And the tree is on the way, and it's going to be even more on the way as things develop. And, well, just wait. One day you're going to thank the tree. Well, it didn't take very long. So when we were looking at the data, so that's the scene that we were seeing. And this to us at the time, it looked like blue sky. Well, not so blue, but sky, right? And that looked like, sky on the top. And then I look at it. We had separate cameras. So I look at my camera in the visible, and the tree is there. Yeah, okay, on the way. Then I look at the camera at the 2 micron, and they're separated. And I'm trying to match the images, and they can't match it. These two images don't look alike at all. Like, this looks like almost like a volcano plume. Lots of structure. That's very smooth, like the cloud, like I see the cloud. And they're completely different. I mean, look, it's the same scale. And I cannot match. I could not find the image that corresponded to that image. But then suddenly I look, and I can see that the tree is there. So the tree is on the way, and I match both trees. And I realize that actually the cloud is all the way there. This is not blue sky at all. The cloud is coming all the way here. So there is a cloud there, and you can't see it. And I only found this because of the tree. And this took a couple weeks after we had the experiment, and Lorraine said one day I would be thanking that tree. And I've been thanking that tree now for over 10 years, right? So really, there was a lot of smoke. We didn't know. There was biomass burning. There was a lot of smoke. And this was smoke. And because of the very small particle size and the geometry that we had, it looked blue. So this is not the bottom of the cloud. The cloud is really here, all the way here. And because 2.1 micron will see through the smoke, we could see the cloud base at that point. So that was the basis for Claim 3D, right? And many of you may have heard about Claim 3D. So it's a proposal we have been trying to push for a while now. And we may never fly it in the US, but the Germans are getting ready. Brazil is getting ready. So they're making lots of measurements in this direction. So if we don't fly, they will. And we will eventually have measurements like that done from space. I have tried from CubeSats. I have tried from all sorts of things. Can't figure out a way to make those measurements in the US. But again, Germans are getting ready. They got funded to do an experiment in the Amazon using exactly the same technique we developed. And they have done one experiment, I think, 2 years ago. They're going to do another one starting this year. And Brazil built some instrumentation in that direction. They're also making measurements. So we'll keep trying. But that all came from that. And then I want to tell you one more story. It's two small stories. You know, and that has to do with what a physicist carries on its pocket. What do you carry? What do you have with you when you travel, right? So it happens I'm going to China, and I have in my pocket polarizer sheets. I have no idea why, okay? So I don't remember. But I had with me polarizer sheets in my wallet. You know, plastic polarizer sheets, right? And it happens that when I'm coming back, and I go to China for a conference, and they bought a camera. I didn't have a digital camera. I bought a digital camera in China, and I'm coming back with a digital camera and a polarizer sheet. And it happens that they give me first class. So I'm flying first class. I don't know why. For some reason, they put in first class on the window. And I'm looking outside the window, and there are these beautiful clouds, flat clouds. And for hours and hours, we see those clouds outside. So I look, I have a polarizer sheet, I have a camera, and a lot of time, right? So I start taking pictures, and I put the polarizer sheet in front of the camera, and started rotating the polarizer sheet, and took 0, 45, and 90. I had an idea about those measurements. Started making those measurements. And, you know, I was trying to see, can I see rainbows? Because I know that rainbows will show up, or cloud balls will show up if you have polarized measurements. So I took 600 pictures. And 600 pictures later, the flight attendant came to me and asked, you know, and she really asked, "Sir, we're all wondering, it's so cloudy outside, you know, it's all overcast for hours and hours. Why are you taking so many pictures?" And next thing I'm trying to explain to her, right? And she goes, "Oh, okay," and she left. And they keep taking pictures, right? I'm taking pictures. And I turn around, and I'm sitting alone in that row, right, on the window. And it's bright, right? And everybody trying to sleep, and my window is open, and I'm taking pictures. But it's first class. They don't complain with you when you're first class, right? So they try to accommodate whatever you need. So next thing I notice, I turn around, and she's beside me holding a blanket around me so that everybody else can sleep and they can take pictures. And the poor woman is holding it. So I went to her, okay, I have over 600 pictures, I'm fine. So we close the window so everybody can sleep, and I started processing the data. And I got this image during the flight. So during the flight, as I was processing, so that's the overcast that I was seeing, right? The polarizer at 0, 45, and 90, and then you process it. And I start seeing the color separation here, right? So very dark there, no polarization. Some strong polarization, white here, and then some colors. This is all through the windshield of the aircraft, so it's not a very good measurement. But nevertheless, that became the first cloudy bowl profile that I ever measured. So from the camera and the polarizer sheet, so, you know, physicists carrying something in the pocket can be useful. That became the basis for HARP. So HARP is the CubeSat satellite that we are going to be launching later this year, you know, to do those type of measurements. But then, I can tell you that what a physicist carries on its pocket can get you in trouble, and in deep trouble, very easily. So this was my second then experience. Same year, I got so excited with the cloudy bowl measurements, right? And then I'm going to try to measure again cloudy balls or rainbows in a trip to Germany. And I asked Dominique, my engineer, right, to build me a device that I can take to the strip and make measurements. They, you know, for some reason, I'm going to fly first class again. And they give me first class. But it happens that TSA security actually did not like the wires and the battery that was coming out of the device that was built like in a week. so that I could take to the trip. And they noticed it, but didn't say anything, so they let me board, right? And as I start to prepare my device, so the police came, and I was escorted out of the plane by 2 police officers, but first by this person with a very long coat that was probably like a bomb shield or something. I don't know. It was a very weird coat that the person was dressing. Escorted me out of the plane. Then the police take me there. After they held the plane for a while, and after a while they let me go back, but I had to fly with 2 flight marshals, one on my side, the other one on the other side of the row. And then in the way back, right, so it's all done. I'm not going to try any measurement in the way back. But I have been, selected for a random check in the way back, just random. And I have, the most thorough check I have ever seen on anyone, but it was just random. So they picked me on the way back from that trip. So it was very interesting. So I'm more careful now with the things that I carry in my pocket. I have a few slides to wrap up, but so this is, my team at UMBC of the people permanent who is there helping us to build things, and they really can build anything, right? And just a few examples. So this is a device that we built to go on the wing of the aircraft, so the open image nephelometer. So we have laser beams going back and forth, and the wing is shaking all the time, and we have to figure out a way to control the shaking of the wing and the laser beam and make sure that the laser beam is hitting the right place, right? And that's just an example of the type of things that we can do with this group. So a device that basically now locks the laser beam, and no matter how fast the wing is shaking, you cannot get rid of it. And then we can do our measurements in the atmosphere thanks to things like that. I'm going to move fast, but these are some of the results from measurements like that. So that open nephelometer measuring phase function as a function of angle, and in this case inside a cloud. And because it's an open system under the wing, you can measure cloud droplets, you can measure ice particles. We also have similar device, and I have shown this many times here, to measure the scattering as a function of angle inside the instrument. So we can bring aerosols inside the instrument and make the measurements. And these are examples with some validation. So theory versus measurement in different wavelengths for polarized measurements and for intensity measurements. So those are all things that we have done and built and designed and create instruments so that we can do those measurements. I want to get here. So this is now going from those in situ measurements to the remote sensing and making that connection beyond, right? So that's the HARP satellite, and I have a model here. So this is actually the 1-to-1 size of the multi-angle imaging polarimeter that you have in the HARP satellite. So it's a CubeSat satellite. It's a very, it looks identical to the original instrument. So this will fly in space, will go to orbit in August this year. And it came from several prototypes, including my first camera, which was not this one, and then a modified camera to do those measurements, and the other prototypes all the way to the one you saw here today. And the inspiration from that comes from, if I'm sampling clouds as I'm flying, I can see all those variations in the polarized field, like showing cloud balls, or in the intensity field. And with HARP, we are sampling very fast so that we can, for every single pixel in the image, determine those cloud ball features that I showed before. So for instance, here is in a hole, right? This is with another simulator. This is in a hole of the cloud where you don't see the cloud ball, and then in the pixel just close by it, where you see the cloud ball structure. So really, we can do the cloud ball measurements over the whole image, even for very variable clouds. So that's the concept that we have with HARP. And then finally, I want to get to air photons. So wrapping up all that, so it becomes all about air pollution, right? Because now we even started a company to build air pollution instruments And so that we can, with everything we learned, now take this instrumentation and make measurements in the field and in different locations. And it's really air pollution measurements. So this is what we are doing here. And thanks to the Spartan network by Vanderlei Martins at the Dalhousie University, there is a network of those instruments that are now spreading all over the globe, making those air pollution measurements, making those measurements in different locations. And again, coming back to the people, I really think I'm, very, very lucky because I'm surrounded by very special people. So these are some of the recent ones, right? And they are, surrounding me at UMBC, at Goddard, or more often Shanna's house, right, where we have several of our meetings and do many things, and also at home. So, have my kids and my wife, my son Rafael, who many of you met, and is now an angel. But really, by being surrounded by these people, is that I think we get the inspiration to do what we do, right, and to work on the things that we work. Thank you.
Is it São Paulo?
That's São Paulo. This is São Paulo. You only have green away from the city, right? And then you have this sea of... It's somewhere, you can't see, it's behind the pollution. Charles.
What didn't you like about working on air pollution? And what was it that ticked you off that you left the exam and wanted to abandon everything?
So air pollution at the time, to me, sounded like, something dirty, right? So something that's not fundamental, something that's not pure in many ways, right? And, you're being educated as being a physicist, and you are seeing all these pure sciences, all these things around that look like they're so fundamental. And the truth is, the fundamental is all around us, right, everywhere, and nature is all around. But I couldn't see it. It took me a while. Paulo, for sure, was the first person who told me, forget about that. Science is everywhere. And look, it's everywhere. It doesn't have to be something in the direction that you're thinking. So really, my advisor was the first person who told me that, and it took me a while to realize it. And in the exam, when I decided that I was basically going to leave and that was it, I was just saturated, right? Because I was still trying to work like crazy to make money to support my family. And I would look at the students in the class. I remember clearly, being in the class and someone teaching something, and I'm struggling to understand what the professor is saying. What the professor is teaching there. I have no idea. I don't know what he's doing. I don't know what he's talking about. And then a student raised the hand, Professor, you have a mistake there, and that's wrong. And how is that possible? I don't even know what he's talking about. And the other student can correct the mistake on the board. So I couldn't understand. I didn't know what was going on. And so I reached a point that I thought I can't do it. There is no way. Now, on the experimental side, I had people like Manfredo and the professor before him that they were amazing, and they was really excited about the whole thing. But took some, guidance, and took some, maybe that fatherly figure there coming there and say, let's go for a coffee and figure it out. So.
I enjoy it very much because I graduated from the Institute of Physics in 1969.
So the picture is more or less from that time. Yeah, it's an amazing place. So
Okay, Nick.
I noticed an interesting parallel, this story you told about your father building this car for you. And all of the kids wanted one, which is sort of like later in life, when you went into the laboratory and started building all of your scientific instruments, a lot of the other scientists coming to you and saying, I'd like one, how do I get one?
Yeah, and that's exactly it. That's the reason we started a company, because in the lab at the university, we couldn't build the instrument for everybody who wanted it. So it's exactly the same. You're right. So it's a very close parallel.
Okay, let's thank Padre one more time.
Thank you.